right, what do you think happens when I wiggle my hand?
It disappears into the bag.
No, it feels good. Actually, look, I get 1, I get 2, I get 3 sponges. But I don't want you to feel bad, you have 3 also. He's got a 3. Let's give him a nice hand.
How do you see that? Can you tell us how you do that one?
Yes, extremely well.
That I like that one.
Can
That's
you
a
keep a
good one.
secret?
No.
Yes.
That's why
Alright, so make sure you take pictures of those notes before we leave today.
Okay.
So I'm going over all.
All right, so do we have any questions? We left off looking at a thermochemical equation, and one of the main points we made in the thermochemical equation is, A, that the little symbols indicating the physical states are important, because if you have a different physical state, it requires a different amount of energy. And so we have to know what those physical states are, and those have to be included in the thermochemical equation. The second point we made is that the thermochemical equation is stoichiometrically related. So that if you have a delta H value for 1 mole of the product, for example, then you may be forced to use fractional coefficients in order to express that thermochemical equation in terms of 1 mole of the product. Now, if the delta H value, or sorry, delta E value is positive, we call that an endothermic process. That was a process whereby energy was absorbed. We'll talk a little bit more about that later. If it was negative, we call that an exothermic process. And that means the system has given off energy. The difference is in the surroundings, what we should observe in the temperature of the surroundings. If it's a reaction that gives off energy, then we expect the surroundings to heat up. If it's a reaction that absorbs energy, then the surroundings will cool down. So what does this really mean? What are these thermochemical parameters and how do they relate to one another? Well, let's talk about it in general. If I'm going to plot an energy level diagram, I have a nice little graph here that deals with energy. Then if I have a system, a chemical system, that system has a certain energy. That energy would be determined by a bunch of parameters. The mass of the reacting species that I have, the temperature, the pressure, all sorts of things go into establishing what the energy of that system is. And so somewhere on this diagram are my reactants. And I could label that energy E sub R. The problem is I don't know what E sub R is. And there's no way for me to determine E sub R. But I know in my heart there is that value somewhere. Now what happens? I do something and chemical reaction occurs. I light the piece of paper and it burns. And I know that gives off energy because I can feel the heat from it. So my products must be lower in energy than the reactants were because I got something out of that. And those products now exist in a certain energy state, determined by the temperature, by the pressure, by the amount of products that I have, yada, yada, yada. And so there's some energy called E sub P. And again, I have absolutely no idea what that value is. And there's no way for me to find out what that value is. But what I can find out, and what I'm most interested in, is I can find out the change in energy that has occurred, or the delta E value, in going from reactants to products. That I can determine. Perhaps a good analogy would be that suppose you're driving through the state of Georgia on an interstate highway. And you don't know, since you crossed the Tennessee line coming south, you don't know how far into Georgia you are. But you know that there are mile markers on this highway. Can you determine how far you go in the next half hour? You may not know where you are in Georgia, but you can tell how far you've traveled in that next half hour. So it doesn't matter where I am in this location here, I can determine the change in energy that occurs. And that's what a thermochemical investigation wants to do, is to determine that change of energy. Now, is it possible to have the opposite situation? Could I have an energy level diagram where the products or the reactants are at some lower energy value and the products end up at some higher energy value? The delta H is still the distance or the difference between those two values, and that's what I'm actually determining. But in this case, the energy has to be put into the system. Here, going from reactants to products, this delta E is coming out. So it's warming the surroundings, making them hotter than they were. The pop bottle was a good example of that. In this particular case, in order to go from reactants to products, I have to put energy into the system. And so if it's coming from the surroundings, then the surroundings are going to get colder. Do I have an example of that type of chemical reaction? I think I do. Here's two chemical substances. Here's a nice white solid that's in a flask. Here's a nice white solid that's in a little vial of some kind. Let's talk about this in terms of energy. Feel these and tell the class they feel like room temperature.
Feel like room temperature.
Are they gonna disappear?
No.
Room temperature.
I know you want to.
I feel like room temperature.
Thank you. Now, and the sideline to this is a very unique chemical reaction. It is not common at all for solids to react with solids. So if I take the one solid and place it into the flask with the other solid, it's quite unusual for two solids to react together. But in this case, if I swirl these around, I'm going to find that the two solids do react with each other. And when they react with each other, they're actually going to form, I hope, a liquid solution. Can you see the sloshing? I might have a little bit too much of one than the other. But there you can see that it's pretty liquidy already. There's definitely been a change that has occurred. Very unique reaction, solid reacting with solid. But my purpose in showing you this is
Really cold.
wow. Don't say room temperature.
It's cold.
In fact, you can see the frost. We'll pass it around so you can experience it. It should stay cold for a while. Just don't open it up or spill it. But this is an endothermic reaction. The reaction absorbs energy. Where's it getting that energy from? From the room. The molecules in the room are going in, and so the immediate surroundings to that system are dropping in temperature, are getting colder. And so cold that it actually freezes water on the outside of the flask, forming a frost. Now, I want to digress for just a moment or two and talk about this concept of this energy. Yes, sir? One of the solids was ammonium thiocyanate, and the other one was a barium hydroxide octahydrate. Does that help? What reacts? Well, when they react, I guess, because God said they should react. But when they react, the waters that are locked in one of the crystal structures are released. And that's what produces the liquid that's in there from the apparent initial solid. Okay, so I want to talk a little bit about this delta E term. It's what we call a state function. A state function is something that does not depend upon the pathway of the chemical reaction. It only depends upon the start and the finish. It's kind of like my altitude, here to my house. Is there a chance that there'll be a change in altitude if I'm standing here or if I'm standing in my living room? Chances are good there's probably a change in altitude of some kind, okay? And that change of altitude is fixed. It doesn't matter how I got home. If I measured my altitude here and I measured my altitude in the living room at home, there's a fixed value that's different between the two. Doesn't matter how I got home. If I got home by taking a route that took me over a huge hill, that's okay, because the altitude difference I'm looking at is here and home. So, what we're saying is it doesn't matter what the energy does in going from reactant to product. We're looking at the delta E, the difference between the reactant and product. Like so. We call that a state function, something that only depends upon the initial and the final condition is called a state function. And the delta E is a state function. A prime example of this is to consider the breakdown of a sugar called glucose. Glucose is a chemical that has carbons, hydrogens, and oxygens. It's known as blood sugar. It's the makeup of most of our carbohydrate food sources. And when we eat those carbohydrates, it's broken down into the glucose. The glucose is stored in our bodies and is slowly released into the bloodstream so that we keep a relatively constant level of glucose in the blood. It's called blood sugar. And so if you're a diabetic, you know exactly what I'm talking about. You take your numbers in the morning. What you're measuring is the concentration of glucose that's found in the blood, and you're trying to keep it at a certain level. The other thing we can do, or two things we can do with glucose, is that we can combust it. You've had combustion reactions in your background already. You looked at the grain elevator the other day. We know that we could put that thing into a device, add oxygen, spark it, and bam! It should react completely. And what are the products of a combustion reaction?
Carbon dioxide and
Carbon
water.
dioxide and water. So in this first left side of the screen here, what I have is a diagram that shows I'm starting out with this glucose and I spark it through a combustion reaction down here, and boom, I produce carbon dioxide and water. It's obviously at a lower energy because if I combust something, it's giving off heat, and I'm getting that heat, so my products must be lower in energy than the reactants. Now, we also know that glucose is a food source. It's what gives us the energy to do stuff. We eat food, that food is stored in us chemically, and the glucose is made available when we need it on demand to do work functions. If I'm going to pick up this pointer, it required me to expend some of my glucose molecules of energy in order to make that lift. Now, the breakdown of glucose is very well known. If you've had some biology classes, you might have gone through this, the breakdown of glucose. If you go on in chemistry, organic chemistry, biochemistry, you'll get this for sure. It's a very complicated process. It is something that, I've tried to diagram over here a little bit on the bottom. It goes from glucose to a glucose 6-phosphate. There's actually a couple of steps that require energy. They make it go up in energy. They are endothermic. And then it produces pyruvic acid at some point. It then goes through a cycle called the Krebs cycle. You might have heard of that if you've had some biology. It's about 37 separate chemical reactions. And what are the end products of the breakdown of this sugar in our respiratory tract? Carbon dioxide and water. That's what we exhale. We are exhaling the glucose sugars broken down that we ate yesterday. And so they end up at some point where we have carbon dioxide and water. But the important thing about this diagram is, look, it doesn't matter about the pathway. It's where we start and where we finish. One step, bam, chemical reaction, or a 40-some step chemical reaction to get us from start to finish. The pathway doesn't matter. The amount of energy we get out of that glucose is the same either way. It is a state function, or what we call a state function. Now, why do we make such a big deal about that? Well, let's imagine that it was not true. Let's just consider the case where, hey, energy is not a state function. What could I do? Suppose I had a system in some conditions I'll call A. And I'm going to move that system to some conditions that I'll call B by a direct path. And let's say that direct path took me 3 energy units, 3 joules or calories or whatever you want to call them, but it took me 3 energy units to go from A to B. Now, let's go from B to A, but by a different pathway. So I'm going to return to A from B by going through this stair-step type approach. And let's just assume that that's a different energy factor. Maybe that's 4 energy units. Now, if I'm going from higher to lower, that means I'm getting back those energy units. That's what the negative sign means, is that it's an exothermic, it's a release. Think about what I could do with this system. If I built such a system in my basement, I could buy 3 units of energy from Georgia Power. Move my system from A to B. Then, let the system come back from B to A by the stair-step process. And what happens? I get my 3 energy units back again, plus an extra one. I could use that 1 unit to power my air conditioner and use the other 3 to go back to B and let it come back again. So what do I have here? I have a perpetual motion machine. I have a machine that is creating its own energy. And we have a law called the first law of thermodynamics that basically says you can't have a perpetual motion machine. And what this establishes is that there is a state function that we call the energy that says it does not depend upon the pathway. Yes, sir.
So basically, if you start at A and you end up with B, it'll always be the same amount of energy no matter how you do it.
That's correct. Energy is a state function. It doesn't depend how I got there. It depends that I'm starting at A and I'm ending at B. The energy's got to be the same.
If you do the A to B thing, or if you put in 3 energy to go A to B, then after you release 4 energy to get to A, it doesn't make any sense.
That's right. Doesn't make any sense, and that's what we're saying. So we played devil's advocate and we said, let's assume that it was something we could do. What would the result be? The result would be an impossibility. And so what we're doing is declaring that this can't be true. I'm going to put a big red X through it. I can do that. No can do. All right. So what do we know? We have a quantitative description of the energy involved in the system when the reaction is carried out at constant temperature and constant volume. Remember, we're in that closed container. In that closed container, we sparked the reaction, gave off some heat, we went to the water, we measured the amount of heat, and we determined what that delta E value should be. From this, we can get what's called a mathematical definition of the first law of thermodynamics. The first law of thermodynamics concerns itself with 2 quantities, heat and work. And so the change in energy is equal to the heat, which is symbolized by a Q, and the work, which is symbolized by a W. Both processes are energy processes. And so what we're finding in the first law of thermodynamics is that the sum total of these things defines what the total energy is. Now, work defined here, we're taking it from physics, is a force times a distance, or a change in distance. Prime example of this is a piston. If you're going to change that collection of gases by pushing in on the piston, then there's been a change in the distance. That's a delta D down there. And so the work is equal to the force times the distance. But force in physics is defined as pressure times an area. We're borrowing some things from physics. If you hadn't had physics before, that's okay. Just take it for granted that this is what we're saying. And so we can define the work then as, if we plug this back into this top equation, is the pressure times an area times a change in distance. Okay, think about this logically. What is an area times a distance? Think of a box. If you had the area of the box and you added the depth or the distance feature, you would have a volume. So the work is what we call actually pressure volume work. So P delta V. And because of the physics and the definitions and the flow of the work and so forth, there's a negative sign here. So our first law of thermodynamics becomes that delta E is equal to the Q value minus P delta V. So let's use this as a starting point. Let's say that however we got it, we don't understand the physics, that's fine. However we got this, here's our first law of thermodynamics that involves both heat and work. The work is called pressure volume work. That's why we have a P delta V term. Now, if I carry out a reaction at constant volume, what's delta V?
Zero.
It's 0. And if that's 0, that whole term becomes 0, which says what? The entire change in energy is equal to the heat. I'll put a little V there to indicate that it's a constant volume. But most of our experiments in the laboratory are not done with constant volume. We use open containers. And so if gases are created or used in that process, they come, they go, and we have what are called conditions of constant pressure. And so we do not have conditions of constant volume in most cases. We have conditions of constant pressure. Well, let's rearrange this a little bit. Delta E is equal to, let's say at constant pressure, but then the work does not change to 0. We have this. Now, if I rearrange this, Q sub P, or the heat that's released at constant pressure, is delta E plus P delta V. So just for grins, just for fun, let's define a new quantity. Let's define a quantity called H and make it equal to E plus PV. And since we called E energy, even though this is an energy term, we don't want to use the term energy because there'd be confusion between the two. So we give this a new name, we call it enthalpy. So H is some new mysterious term called enthalpy. And what does H equal? Well, it equals E plus PV. Now, if Q sub P is equal to delta E plus P delta V, then look what I can do. Q sub P is equal to, how do I get delta E? Diagrams on the other side, on the other board. It was the change between the products and the reactants. Whenever we use the delta term in chemistry, we most frequently think of that as the final minus the initial. So in a chemical reaction, what would that be? What's the final? The product. And the initial? The reactant. So instead of putting delta E here, I could say, hey, this is the energy of the products minus the energy of the reactants. Plus P. Now, V, delta V, is the same thing. It's the volume of the products minus the volume of the reactants. Okay? Lost, huh?
What is, so Q is heat?
Q is heat.
So heat
W is
equals, the heat equals the change in the energy. Plus, what's P?
The work. Pressure.
The pressure. Okay.
So the P is what? Like you said, pressure.
It's the pressure that's applied to this type of system.
Okay, so it's not the work, it's just pressure.
P delta V is the work.
Okay, I get
P
it.
is the
But P
pressure.
is just pressure.
So all I've done was expand this by definition of what a delta term is. All right? Let me expand this.
So everything you're showing us pretty much means the same thing, or it's related to each other.
Yeah, it's just a derivation. Remember, I made a definition here that we're going to come back to in a second. But this came from the first law of thermodynamics. In the first law of thermodynamics, if I'm at constant volume, then this V term disappears. And I have only this, so that all the energy at a constant volume process is converted into heat. But in a constant pressure process, there could be an expansion of a gas that performs some work function. So I have to include that into the energy. And what I'm trying to do is isolate the heat from this. Makes sense? Good. Okay, just rearrange terms a little bit. Just move this guy over here, this guy over here. All right? Here's a little mathematical magic. If I have minus ER minus PVR, can I do this? But, what is this term right here? EP plus PVP. By my off-the-wall definition of something called enthalpy, that is the enthalpy of the products. Remember, it's a type of energy term. Minus, what's this term? That's the enthalpy of the reactants. And what would the enthalpy of the products minus the enthalpy of the reactants be equal to? Delta H. So, the heat at constant pressure is what we call delta H. All of this was designed to show you that there's some logic behind this term called enthalpy and the fact that this is the one we use most frequently.
How are you doing that?
Because most of the systems that we deal with are at constant pressure. And so it's incorrect for us to talk about the change in energy. We define it as change in enthalpy.
So pressure and energy and
Wait until you get to.
Yes. Yes, the energy, the heat, the work can all be measured in the same unit. They have to be in order to be able to state that they're equal.
It's where you're substituting all that stuff. You know, you have to substitute stuff. There's differences.
All right, questions?
But it's
What are you supposed to get out of this? A headache.
Right,
Was I successful there?
a migraine,
A
a
migraine.
headache.
B, all I want you to get out of this is the fact that we deal mostly with a term called delta H. And that there's a foundation for that. That it's related to the energy. It's not necessarily the same as energy. We call it enthalpy because the conditions are different.
So we don't have to memorize every different.
No.
Okay.
No, you don't have to do this.
So delta H is enthalpy,
Delta H is the change in enthalpy.
the change in enthalpy.
Okay? And it's also what we would call the heat of the reaction. So in most of the stuff we do from now on, we will have a thermochemical equation and it will have as part of it a delta H term, not a delta E term. Because most of the stuff we do is all going to be at constant pressure. Well, it's not so bad.
Is there, what is the other one, entropy? Is it entropy?
Entropy you'll get next semester.
Oh, okay.
You don't have to worry about that.
Here, girl, sit down.
Yeah, it'll come fast enough. Now, remember how we would do this. We would do this in what's called a bomb calorimeter. If we do it in a bomb calorimeter, we're actually getting a delta E value. Now, you're going to do this in the laboratory. Tell me you haven't done the calorimetry experiment yet.
We haven't.
No? You're going to actually do an experiment that deals with what we call calorimetry. Calorimetry is the investigation of a chemical reaction to get a delta E or a delta H term. In your case, you're not going to use my perfect insulated cooler that blocks all the energy flow, but you're going to use something that's very, very effective. And that very, very effective is a styrofoam coffee cup. A styrofoam coffee cup, if you think about it, is a very good insulator. Because how can you tell that? You pour boiling hot coffee in there and then you pick it up.
Mm-hmm.
If that were boiling hot coffee and the styrofoam was not a good insulator, could you do that?
No.
You put it into a glass or a metal cup, could you just pick it up like that? Not very easily. That means that the styrofoam is an excellent insulator. And in fact, we use 2 styrofoam cups. Oh, this could be trouble. Something like that. Oh. So we place 1 styrofoam cup inside the other styrofoam cup. So there's a double layer of styrofoam which acts as a very effective insulator. And then we put a lid on this, coffee cup lid. And then we put a thermometer in here and a stirring rod. And you're going to put chemicals or something into this coffee cup, and you're going to measure the temperature change that takes place. And that something is going to be a solution, so it's going to be primarily water. And so we'll be able to monitor the temperature flow, because remember the specific heat of water is 1.0, no it's not, it's a 1.0 calorie, it's 4.184 joules per gram degree centigrade. What that means is that if I had 1 gram of water, and I'm going to change its temperature by 1 degree centigrade, from 14 to 15 degrees centigrade, it's going to take me 4.184 joules of energy. Okay? That's a measured, known, recognized, tabulated value that we can now use in our calculations. So here's a question. How much energy is needed to heat 300 grams of water from 25 degrees centigrade to 75 degrees centigrade? The formula for this is that the heat that's needed to change this water is equal to its specific heat times its mass times its change in temperature. Now remember, specific heat is a joule per gram degree, so it makes sense. If I multiply this by a mass, the grams will cancel. If I multiply it by a temperature change, the degree centigrade will cancel, and I'll be left with a joule, which is an energy term, which is what I'm looking for. So in this case, it's 4.184 joule per gram degree centigrade. I need to know my mass of water. Piece of cake, it's 300 grams given right in the problem. I need to know the temperature change. Not so easy. I actually have to do a subtraction to get that. It's 50 degrees centigrade. So can I calculate the number of joules that are necessary for this to happen? and I get 62,760 joules, or about 62.8 kilojoules.
That's the equation we're gonna need to know.
So if I were doing this experiment and I had in my coffee cup calorimeter 300 grams of water and I observed a temperature change that went from 25 to 75, the heat that was released by whatever source that was in this particular system would have been 62.8 kilojoules. Now here's the problem. The water is not the only thing that absorbs energy. If you look at our system, we have what? We have a thermometer in there. Will the glass of the thermometer warm up?
Yes.
Sure. Will the liquid in the thermometer warm up? I hope so, because that's what's causing it to change its position. Will the stirring rod warm up a little bit? Will the cup warm up a little bit on the interior? Yeah. So we have to consider what the entire system is doing. And so to do that, what we generally do is carry out what's called a calibration experiment and determine what's called a heat capacity. And the heat capacity is for an entire device. So it's not for a single substance, like specific heat is for a single substance. The heat capacity is for an entire device. So we want to find the heat capacity of our calorimeter, and it would be expressed in joules per degree centigrade. We don't have to worry about the mass here because we're going to keep the mass constant for our calorimeter all the time. We use the same calorimeter, the same thermometer, the same stirring rod every time we do the experiment. And so that's a constant. So we're going to determine the heat capacity of our coffee cup calorimeter. And this is what you will do in the laboratory. This is a 2-week experiment, and this is what you will do the first week. You're going to do that by mixing together hot water and room temperature or cold water. When you put hot water and cold water together, what happens? There's a transfer of energy from the hot water to the cold water. Ideally, what happens? The energy lost by the hot water is transferred to the cold, and they meet at some intermediate temperature. But in reality, when we put that hot water into the cold water absorbs some of the heat, but so does the stirring rod, so does the thermometer, so does the coffee cup. So what you're going to do is to calculate how much energy did the hot water lose, how much energy did the cold water gain, and if there's a discrepancy between those two, where did that extra energy go? Into the calorimeter. And so you're going to be able to determine what the energy value per degree centigrade is for your calorimeter. I'll give you a little heads up, that experiment usually gives you horrible results. Okay? Horrible results. So you need to be as careful about it as you can. I mean, people get negative values when that's physical impossibility, values that differ by like 1,000% from one another. So you just need to do it very, very carefully. The good news is you get to use a partner in the laboratory, because one person has to watch the temperature while the other person is stirring and so forth. All right. Questions?
I didn't pass the final.
I'm sorry?
I didn't pass the final.
Did I not pass one today?
No.
Are there practice problems like that online?
I don't know. There's some in your book, for sure. Are there some online? Possibly. You have to take a look. If not, let me know. I'll see if I can find some for you.
Can we set up our study sessions?
Yeah, there's been some requests for some study sessions on a regular basis on Wednesday.
I can do Tuesday, Wednesday, or Tuesday, Wednesday, Fridays.
Wednesday and Friday works pretty good for me, usually, in the afternoon. 1:30.
Friday?
Should we say at least an hour? This is a regular basis type of thing. And we'll meet down in the University Center at the tables down by Pizza Hut.
We'll start
area.
this starting after spring break.
Yeah, we'll start after spring break. Anybody want to meet next week during spring break? One person? If my other class decides to meet, I'll send you an email and we'll do it. Otherwise, maybe you and I can meet at a coffee house somewhere, start some rumors. Get me fired in my last couple of years.
Oh, God.
So remind me to do this, because I have to announce to my other class that this is one of my normal office hours here, that I'll be doing it down in the cafeteria, and I'll invite them to come down as well.
Thank you.
All right, let's try a problem.
You say 1:30 at 2:30? Yeah.
Is that okay?
Kilojoules per gram or kilojoules?
Where are we? Here,
Right there. What is that?
kilojoules of heat.
So that's an hour.
Just using shorthand.
Yeah, that's okay.
What is after it's 26.3?
8. Wow.
What are you guys trying to say? Print this damn thing up. All right, so 1 gram of benzoic acid. Benzoic acid is a typical standard that's used to calibrate calorimeters. Produces 26.38 kilojoules of heat. But this increases the calorimeter temperature by 4.857 degrees centigrade. What is the heat capacity of the calorimeter? The heat capacity of the calorimeter is the heat over delta T. If you look back in your notes at the definition I gave you for heat capacity, or the unit anyway, it was a joule per degree centigrade. We didn't have to worry about the mass. So this problem is easily solved. The heat capacity is simply the heat for 26.38 kilojoules over the temperature, 4.857 degrees centigrade. So I get 5.431 kilojoules per degree centigrade. Now, be careful here. Make sure that you're talking about a delta T. Okay? You're not going to use the first temperature you take or the second temperature you take. You're going to take the difference between those values, a delta T. Now, a lot of times in chemistry we deal with Kelvin. All right? Do we have to deal with the temperature in Kelvin here? And the answer is no, because actually the size of a Kelvin degree and the size of a centigrade degree are identical to each other. So whether we record a delta T in centigrade or Kelvin makes no difference. The change is the same, because the Kelvin temperature is just the centigrade temperature plus 273, so it's just a translation on the number line. And so it fixes that. Now, this is a mathematical expression in 3 variables. Give me any 2 of them and I can solve for the third. So after you get your heat capacity of the calorimeter in your laboratory experiment, you're going to do another experiment where you calculate the delta T and you're going to be looking for the heat that that calorimeter absorbed as part of the chemical reaction so that we can include it into the calculation of what's taking place. Well, remember, when a chemical reaction occurs, you're going to see some change in temperature for the system.
Then that correlates back to the equation.
But you have to also account for the amount that has gone into changing the temperature of the calorimeter.
Is the thing, what is the change?
Again, the molecular weight, why did you do that?
What is the
Force of habit.
heat
I
capacity?
tend to give the molecular weight all the time, whether you need it or not, so that you don't have to look it up. It may be in this particular problem we didn't use it, or maybe in part B of the problem, we would need it. If we were trying to write the thermochemical equation for this reaction, we would need to know the mole value for benzoic acid, and so you would need to know how much that was going to be.
Change into.
Okay. We don't have much time for this, but maybe you want to copy it down and try it. We'll start with this on. Even though we've had snow days, I know you've been working hard on chemistry lately. I'm giving you next week off.
Hooray.
I'll take it, no need to thank me. But you better come back that following Monday ready to go. And I would suggest strongly that you not take the week off, but you look up on it as an opportunity to get caught up in a lot of chemistry that you may be having some trouble with. So a student mixes 50 milliliters of 1 molar HCl, 50 milliliters of 1 molar NaOH in a coffee cup calorimeter. Temperature of the solution increases from 21 to 27.5. Calculate the enthalpy change flow. That's the new cool way to say for the reaction in kilojoules per mole of HCl. Assume that the calorimeter only uses a negligible quantity of heat. So basically that's saying that what? The heat capacity of the calorimeter is 0. Total volume is 100, the density is 1 gram per milliliter, and specific heat is 4.18 joules per gram Kelvin. And we will start with that puppy next time and try to finish chapter 15 and get into finish chapter 5 and get into chapter 6, so we get on to our second hour exam without too much more delay.
So the second exam is on chapters 4, 5, and 6.
And the stoichiometry part of 3.
Okay.
Yeah, it'll be a mother.
Do you have a I don't know what the word is, like a cheat sheet of the
Hey, anybody lose an umbrella earlier this week? Been toting it around. No?
of the formulas that we're gonna need to know?
Do I have a list?
Like a list of the formulas
No,
that we
do
need
you
to
have your
know?
textbook?
I do. Well, not with me, I'm sorry.
Oh.
Yeah.
If you look in the back of the chapters of in the textbook,
Uh-huh.
they usually list key equations
Okay.
in a separate table. See if that
Okay.
gives them to you.
Thank you. Thanks, Nathan. That was a good idea.
I keep asking myself whose big idea it was to go back to school.